Kevin's ready and eager and raring to go. So over to you, Kevin.
Thank you, Dave. Good afternoon. So my talk today involves the topic ultra-thin S355 strip steel microalloyed with vanadium. I'd like to acknowledge my co-authors, Matoya Vanette-Shalema, Ian Stein, and Carl Kutsia. We've just finished, completed this work. We sent a final report off to Vanatech, and they have it in their possession. Okay, so there's a demand for thin, and I'm talking 1.5 millimeter thick S355 structural material with yield strength above 355 MPa for the steel and tubing and piping industries. And the local demand here in South Africa is only 0.5% of global production, which in 2021 was estimated to be 15 to 20,000 tons per year. So doing the maths, that actually works out to quite a bit of tons globally. So low carbon is preferred for good weldability, but of course it involves lower strengths. Hence, traditionally, niobium titanium steels have been used for these products, but niobium increases strength. Well, and the reason why is because niobium increases the strength via carbon nitride precipitation during rolling. It causes a delay in crystallization and of the austenite, with a resultant increase in final strength. But niobium decreases hot ductility during continuous casting, if not cast properly, increases roll forces during hot rolling, has width limitations, and often deteriorates shape, particularly in thin material. Vanadium, on the other hand, has a greater solubility in austenite, causing less precipitation during hot rolling, has almost no effect on the crystallization, as with carbon manganese steels, with resultant lower forces. Most vanadium carbon nitride precipitates after hot rolling to achieve strength in these grades. Also, in thin strip, you have higher heat losses, which increase roll forces and can lead to unstable rolling. We have more precipitation, strengthening, and strain accumulation when rolling below the so-called no crystallization temperature, or TNR. This is particularly relevant in niobium steels. So we expect that vanadium nitrogen grades will reduce or avert this problem. So the objective primarily is to develop an as-rolled, thin gauge, less than 2 millimeter, low carbon, medium manganese vanadium nitrogen steel on a conventional hot strip mill to EN S355MH as an alternative for the light structural and tubing industries. We also aim to compare the properties and sort of rollability with extra thin niobium steels. So this would be the going to procedure now. The chemistry, the specified chemistry for S355MH is the top row of the top table, where you have quite a bit of niobium, titanium, and vanadium license, fairly, and a bit of nitrogen as well. But our aim chemistry is highlighted over here, where we have about 0.55 vanadium and 100 nitrogen. And I'll tell you why we did that, why we chose this chemistry just now. These are the second table is the tensile requirements for the MH and the JR equivalents on S355. The only difference being the UTS range, that's being somewhat lower on the MH versus the JR, where you need a minimum UTS of 510 megapascal. Now, we chose this chemistry based on Boglodowski's formula, based on a lot of global data that relates the yield strength of ferroperlite steels simply to the manganese, vanadium, and nitrogen content. In other words, it's basically independent of processing variables, and shown as follows. So wanting to be about 30 MPa above the minimum of 355, in other words, 385 MPa. This would be the required amount of manganese, vanadium, and nitrogen. So we use that as basis. We then did full-scale trials casting full thickness slabs. Final thickness rolled down between 2.5 down to 1.44 millimeter. For the vanadium nitrogen steels, width in the region of 1230 millimeters. No transfers or longitudinal cracks were observed during casting, which was good. The initial thickness at 2.5 had mill exit temperature of 860 and a core temperature of 65. When we went down below 2 millimeters, we then dropped the F7 was dropped to 840 Celsius, core temperature at 575. Also, early run-out table cooling was applied. Tensile testing to ISO 6892 was applied both in transverse and rolling directions in some steels to look at isotropy, but in the rolling direction and you know, for the bulk of the testing. Light optical microscopy or LOM was undertaken using a 2% nitrile etch, and then selected EBSD on 2 vanadium nitrogen coils, 2 niobium titanium coils. Okay, so this is the microstructures that we achieved. So in A here we have a 1.6 millimeter vanadium nitrogen, quite a fine grain size actually, 4.5 microns, after finishing it at 840 and coiling at 600, 4.5 microns. As you go thicker, okay, B and C are both 2.4, where in the majority of cases we also have a polygonal ferrite pearlite structure, but coarser, 5.9 micron in this case. There was an incident where we actually, using the same processing parameters, observed a more circular structure, and this was attributed to you know, industrial conditions, some coils being subjected to slightly faster cooling, which would be conducive to a circular morphology. These samples were taken at the 40 width in the transverse direction. This compared to, although they're quite fine, they were always coarser than niobium steels. For similar thickness, this is niobium titanium steel, 1.6 millimeter on the left and 2.5 on the right. Despite even the higher coiling temperatures in the niobium steels, they were still finer than the vanadium steel. That's because of control, easier controlled rolling, stronger delay in crystallization, more substructure, more nucleation sites, ferrotransformation for a given set of finishing conditions. Just another observation. These are structures in the vanadium nitrogen steel of 1.5 millimeter, going from the edge of the strip towards the mid-width. So you have edge, quarter width, and mid-width. We have a rather fine structure, still polygonal ferrite, but very fine towards the edge. So expected to have somewhat higher yield strength in this region. Looking at the tensile properties, this is the yield strength in the vanadium steel compared to niobium titanium. The white symbols of vanadium nitrogen and the red symbols of niobium titanium. So this is yield strength at specific coil temperatures, different final thicknesses. You can see strength in both steels well above S355MH in all gauges, F7 and coil temperature conditions. Okay. The vanadium nitrogen steel at 600 degrees was very similar to that as predicted by Gladowski's equation, 385 megapascals. But what was interesting was as we dropped the coil temperature from 600 to 575, there was a distinct increase in strength, about 25 megapascals. Okay. That's attributed to, a coarser vanadium carbonitrile at 600 compared to 575. Interestingly enough, there was no influence of coil temperature on the niobium titanium steel. Over here it was 65 and there's 600 and 575. You can see they're relatively constant. UTS, there's a lower and a higher limit. You can see it's comfortably sitting in the middle on the MH spec. However, and it was relatively unaffected by process parameters. However, The it would have been first prize to have also achieved the JR spec, where there's quite a big market as well. Minimum UTS of 510, so it's absolutely borderline. So we would not be able to satisfy that spec, and additional manganese, or indeed vanadium and nitrogen, would be required. The higher manganese being preferred because of the danger of too high a vanadium nitrogen content and too high volume fraction of vanadium nitride would compromise transverse cracking during casting. The A5 temperature comfortably above 22% minimum, so there's no problem there. Interestingly enough, on the thin material, 1.5, 1.6 millimeter, the vanadium nitrogen grade shows superior elongation, well above 30%, 30, 35, whereas the niobium steel was in just 27%, so there was an improvement there. Okay, so properties in the transverse and rolling directions, they were rather similar in both steels, actually. If you look at transverse direction red and the rolling direction white, you can see there was one exception, steel 11, that is unexplained, but relatively, we have here yield strength, UTS against coil number, and then yield point elongation and end value. The end value was well above the specified minimum, being higher in the rolling direction than the transverse direction in both grades. And it's also the vanadium, nitrogen, niobium, titanium were rather similar in value. The yield point elongation, which describes the non-uniform deformation region after yielding, it affects the quality of forming and the extent of strain aging. You can see that, so here we have, here's the key over here. This is 625 coil and 575 coil on all the graphs. So as the coil temperature drops, you have more vanadium and carbonate and nitrogen in solution, which increases the yield point elongation, as well as we're also moving towards thinner material from left to right. That also gives you a finer grain size and will also increase the yield point elongation. What we did find that at a given coil temperature, 625 degrees, that the niobium steel was comfortably much higher than the vanadium nitrogen steel, which is a benefit in the vanadium steel. You don't want too high yield point elongation. It probably demands a temper rolling exercise to get rid of it for certain applications. This is just another representation of yield point elongation, zooming in on the yield point elongation area of these full curves over here. You can see the vanadium steels have a distinctly smaller or shorter YPE region than the niobium steels. Okay, a little bit of EBS. Not my strong point, texture not being my strong point. However, thanks to my colleague, Mr. Kutsia, who did this for me, we had inverse pole figures for 2.5 thick vanadium nitrogen steel and a 1.6 millimeter thick on the bottom. You can see there's a significant decrease in the 101 fiber texture component. The green one is distinctly reduced the thinner you go, which increases the the 001 and the 111 texture. That, please ignore that 101. That's an error over there. Now, these textures are all advantageous for formability. The 001 being the GOS texture is highly advantageous for the formability in high-strength steels. It facilitates shear deformation mechanisms and leads to improved stretchability and ductility during the forming process. The 101 promotes specific grain orientations that facilitate deformation mechanisms and strain distribution during forming processes. And the gamma fiber promotes grain structures, and isotropic behavior, also leads to good mechanical properties and enhanced ductility. So the full interpretation is still, we need to go into this a little bit more. but you can clearly see how the 101 has decreased the thinner you go. The same result, interestingly enough, was found in the niobium titanium steel, albeit the niobium titanium much finer, as you can see. If I have to compare the two sets over here. So this one would be for 2,6, and this is a 1.7 over here. Yeah, so I don't want to discuss this anymore. It's grounds for further work. But we thought that interesting, rather interesting finding, the 101 being reduced. Over there, yeah. Because the F7 and core temperatures were not exactly the same in these tests, we could not firmly establish their influence. Okay, so this is a force and mean flow stress analysis taken using mill logs in industrial conditions using the Ford and Alexander equation for 3 different steel types: the carbon manganese, the vanadium nitrogen, and titanium. You can see that there's a plot of mean flow stress here, force per unit width, temperature, applied strain, and strain rates. This is the Ford and Alexander equation used to calculate mean flow stress from mill data, where W is width, LD is the contact length, and that's the arithmetic mean of the in and outgoing gauges. Strain and strain rate are calculated using the standard integrated average formula. It's a function of speed and incoming and outgoing material and flattened well radius. You can see, as far as the mean flow stress is concerned, I just want to bring to your attention that the vanadium nitrogen steel was wider and rolled at lower temperature, indicated by the blue curve over here, on the thin material, than the niobium titanium steel, which was only 1 meter wide, whereas the vanadium nitrogen was 1,230 millimeters wide. You can see that despite those differences, the mean flow stress was very similar, and the force per unit width was actually lower than the niobium steel. So that boded well for one of our objectives, was to roll wider, wider material. So that objective appears to be satisfied. We're still well below the limits of this particular mill. Okay, so the most common defects was similar to those found in niobium titanium shaped strips, and that was pinches. Okay, that was about the only shape defect that we observed. Now, pinches involves the transversal flow of material across the strip, which causes uneven flow in the rolling direction, and non-uniform longitudinal stresses over the width that may affect the final shape. It's not restricted to any particular steel type, though, or rolling practice, but it's found mostly in thin high-strength steels. And that is what we did find. We found similar frequency of this defect in both niobium and vanadium steels. Other than that, no other shape problems were reported. So the conclusions are the tensile properties of this particular chemistry on a conventional hot strip mill conforms to S355MH, but falls short of the JR spec. Okay, sorry. The polygonal ferrite matrix is finer in a 1 millimeter strip after coiling at 600 than in thicker material. And then also for a similar gauge, however, the ferrite grain size, I think, in the vanadium steel is coarser than niobium titanium steel. But I think that is well known, and we just have to accept that. Reducing the coil temperature to 575 from 600 increases the yield strength by 25 degrees, which is, not to be ignored. There were only marginal differences, though, on UTS and elongation with coil temperature. UTS and yield strength were similar in both directions. Rolling and TD was 0 and 90, suggesting a fair degree of isotropy. Yield point elongation increased in thinner strip due to finer ferrite grain size and perhaps more solute vanadium and carbon nitrogen. The yield point elongation was lower in vanadium nitrogen steel than niobium titanium steel for a given thickness and a given core temperature. EBSD showed a significant decrease in the 101 fiber texture component, thinner strip of both vanadium nitrogen and niobium steels, and towards a larger distribution of those two fibers, of those two textures. Slower speeds or lower strain rates restrict roll forces, allow stable rolling of strip to at least 1225 millimeters wide. And then change in roll force and change in flow stress, which can lead to rolling instability, were not really observed under the conditions that we trialed the material. And above 900 degrees, nodal titanium is very stable. Below that, instability starts creeping in. Whereas in vanadium steel, you can actually roll down to lower temperatures, or down to at least 850 for fairly stable rolling. And poor shape, generally absent, but pinches were experienced at a similar frequency to that found in thin niobium titanium steel. Right, thank you. That concludes my talk.
Thank you very much, Kevin, for a good, clear talk. Any questions or comments on Kevin's presentation? Just a sort of question / query from me, Kevin. Notice that the vanadium steel seemed to be more sensitive to coiling temperature than the niobium steel. Though you met the yield objective in all cases, but the vanadium steel seemed more variable. Is that likely to be a problem, having a yield strength which is more sensitive to coiling temperature than for the niobium steel, or is it something the mill can live with?
No, I think, thank you, Dave. I think, remember now, the bulk of vanadium precipitation under hot rolling conditions will occur after rolling. And that's where the strengthening really, kicks in. Of course, you can, there is some grain refinement and some precipitation in austenite that can occur that will contribute. But I think the bulk of the strengthening occurs due to precipitation after rolling. So, that variation of 25 megapascals could be due to the volume fraction variation in the last passes. But I don't know. It didn't seem to have any stability issues, but it might contribute to variation in final purposes. Whether it's a problem or not, I'm not sure. We haven't done too many, bulk production will eventually tell.
Yeah, but I guess in general, Kevin, we're saying that the vanadium steel can be rolled substantially wider than the niobium steel, and
yes,
it's
yes.
rolled over a wider range of temperatures. So that's... Yes,
if I have to, one of the biggest take homes from this work is yes, the width is always an attractive. The wider is always more attractive, isn't it? Wider and wider with good shape, yes.
Okay. Okay. Any other queries or comments for Kevin? Okay. Well, thank you very much for that, Kevin. And again, it looks like a very positive result. So thanks again.
Thank you.
Okay, our next presentation is from Professor Sabajit Banerjee at Texas A&M. So hello to you there.
One quick point, Dave. I don't know. I thought Kevin's presentation was fascinating. If you might be able to share, if Kevin or you might be able to share a copy of the report, just so that especially the last point about temperature, Kevin, might be something we put in our model about rolling broader